I'll hope it'll continue to report. A quiz on Friday. We're a few weeks off of our next exam, so I should be studying all along and try to do problems. Like, we didn't have that homework yesterday that was due today, but that doesn't mean we didn't do lots of important stuff, right? Ice tables and things like that. So please be practicing those odd problems in the back of your book. So quiz on Friday, and then we'll have a homework due on Wednesday at 7 a.m. And then I have office hours today. It's not showing anything. Hold on, give me a second. I think there's a play button I need to do here. Thank you. Okay, and then I have office hours today from 1:15 to 3:15. And as I've said before, tomorrow I've got some availability in my schedule. I'm not going to give you any specific hours, but if tomorrow you want to come and meet me, send me an email. We'll figure out a time that we can both meet. I'm happy to talk to people on Google Meet as well. Okay? Questions on what we're doing with the class? All right. Now today we're going to talk more about acids and bases. And we're really going to be talking about strengths. Most of it's going to be strengths of acids and bases. And we're going to get some tools so that we can look at compounds and we can say, that's a strong acid, that's a weak acid, that one's stronger than that one. That's the sort of stuff we're after here. And so in terms of that, I want to remind you of this figure we looked at in the last lecture that talked about the strengths of acids versus their conjugate bases. So as the acids get stronger, I'm going to remind you that the conjugate bases get weaker, right? So we have a very weak conjugate base, that means its corresponding acid. Or if I have a very weak base, its conjugate acid is very strong. And the reason why that's the case, we want a different explanation. This is one of the things, so Shetly's principle, right? We've talked about that. I want you to apply that as often as possible. We can also apply thinking about energy. So these are very stable. Just like noble gases are very stable, right? They've got the number of electrons they want. They've got electronic configuration that makes them very stable, very happy. They don't want to change. Same sort of things for these conjugate bases. They don't want to pick up, I can personify them, which I'm going to. They don't want to pick up a proton or grab an H+ because they're super stable and happy as they are. All right, so let's remember that inverse relationship between the strength of an acid and its conjugate base. Okay, and then I want to show you, let's see. I think we'll look at metal ions. So there's some things we can think about that might make acids that you might not have thought about to begin with. So here's an example from your book. This is when you go ahead and you take aluminum 3+, right? Aluminum is going to be +3 based on its position on the periodic table. And you drop it in water. And when you do that, it's got a +3 charge on it. Let me go ahead and they've got this +3 charge written right here. The whole thing is +3, but really it's coming from that aluminum, because that's what our charge is on aluminum. And when I've got this +3 charge here, I've got these bonds to all these waters, right? Those bonds to the waters, if we think about it, if I drew one, I'd have my aluminum here, okay? My aluminum has this 3+ on it. And then it's going to get a bond with water that looks like this, right? Okay. Charges are going to be a little bit funny here. Let's go ahead and I'm going to erase this just for now. We'll just remember it's kind of there. 3 bonds on, and the water, if we think about water coordinating with an aluminum, we've got these electrons on my water. Forgot a pair of electrons. And so let me draw my water really weird to make it fit. But the way we're getting these bonds to the aluminum is that these two electrons on the water are going to be going in and making a bond, okay? Maybe not a full bond, that's why it's dashed like that. You could think about it sort of like a hydrogen bond, right? This is very positive, okay? But let's go ahead and think about that as a covalent bond right there for the moment. Or dash bond, either way works. So you've got this big +3 charge and it's pulling on these electrons. Why would a plus charge pull on electrons? Yeah. Yeah, electrons are negative, right? And so the positive charge is attracted to the negative charge, or the negative charge. The electrons are the things that are going to move. So what you can imagine then is if I've got this strong pull of electrons that way, right? That we're going to kind of pull electrons away from the oxygen, and the oxygen is going to want more electrons, and it's going to make it easier for these electrons to pop onto the hydrogen, onto the oxygen, and the hydrogen leaves. And then we'd end up with Al. So here, if I'm ignoring the positive charge on the aluminum, then I would end up with this. I'm just doing it that way to have my charges balance across this equation. This is an equilibrium, not a product-driven reaction. So do you see how adding something positive to water, even if it seems weird and there are no protons around, you're adding that on it, there are protons on it, that you add that aluminum to water, it interacts with water, and it can make an H+. Okay, yes?
Could you explain what the red arrow is doing for the
This
other
one?
The other one? On the H and the O.
The H and the O.
Yeah, that red arrow.
Let me do this. That's a good question. It's particularly a good question because I'm not sure which red arrow you're talking about. So I'm going to make this one a green arrow because there are two different arrows doing two different things. Are we still talking about the red arrow?
Yes.
Okay, great, good question. So what's going on with this red arrow here? This red arrow is coming from the bond. There are two electrons in this bond. These two electrons come out of being shared between hydrogen and oxygen, and they pop onto the oxygen. And now the hydrogen has no electrons, so it becomes H+. And then if you look at here, I drew an extra pair of electrons on that oxygen.
Okay.
Does that make sense?
Yeah.
Okay. You are not going to have to draw these arrows, but they're good for explaining things, so I'm putting them in. You will have to draw them in organic. Yes?
So you said that it's not a complete covalent bond, but is it just an IMF that's strong enough that it's able to like pull the electrons so that it,
Yeah.
okay.
I'm kind of saying covalent and non-covalent, and I'm being wishy-washy about it, but the upshot is there's a positive charge here. It pulls electron density from here, and if you're pulling electron density from here, you're more likely to pop off a hydrogen. Yes?
I always thought it was where like the arrow went from the more positive to the negative one. Would it go from aluminum to oxygen? Or like why does it go?
Right. So that's a good question. So there's a big positive charge over here. But what I'm trying to show you is electron density being pulled that way. Okay? So when we draw these arrows, the arrow points to where the electrons are being pulled. And then I might be better off this positive here. Yeah, there's a partial positive here. There's also a bunch of positive over here as well. But these arrows when you draw these arrows, you're showing where the electrons are going. Good questions. Anybody else? Okay. So that's how we could have, I could dump metals into solution and I make that solution acidic. Now, in terms of that, we can think about the strength of a conjugate base. There are no metals up here, right? But we can mix that with thinking about the strength of conjugate bases, and those are metals, right? They were positively charged. I can put metals together with non-metals, right, to make salts. And so when you dissolve a salt in a solution, depending on what's going on or what the ions are in that salt, right, positives and negatives, that solution will become acidic or basic, or it'll stay neutral. Okay, and so we can think about that sort of thing. I can make this a little bigger, but I can't do much else because I don't control the font. But I've got this table from your book, and I want us to be able to use this table to rationalize or figure out whether dissolving a salt in solution would make something acidic or basic. Okay? And I will give you this table. I just want you to use it. All right? Now we're going to also talk about some trends in a bit, so you might have to rationalize something without the table. But we're not there yet. All right, so what we've got here is various effects here. So if we have cations, what this says, I have cations that are from group 1 or 2 except beryllium, right? So groups 1 or 2 are the first 2 columns on the periodic table. When they dissolve in solution, they don't have really an effect on acidity. Okay? All right. Anions from our strong acids. So I haven't worried much about the perchlorates, but we've got chloride, bromide, iodide are the conjugate bases of strong acids, right? Hydrochloric acid is strong, hydrobromic acid is strong, hydroiodic acid is strong, sulfuric acid is strong, nitric acid is strong. Okay, we've got our perchloric acid, etc. So they're all strong acids. They're going to have very weak bases. If they had strong bases, those bases would pick up protons out of solution. They no longer be acidic. Strong acids, right? Remember, these things are inversely related. So these don't have a big effect. Then we have a number of plus charged things that do actually influence water. Okay, do cause H plus to be produced in water, and that's based on the effect we saw above. I mean, ammonium is just going to give up a proton. It has a proton, right? But these other things, they interact with water, and they make it easier for a proton to pop off of it. And then we have weak conjugate bases of weak acids: hydrofluoric acid, acetic acid, fluoride, acetate. We know that second proton coming off of sulfuric acid is also a weak acid as well. So those things, you dump them in water, they're going to pick up a proton. Okay, and they're going to make it more basic. All right, so what we've got is we've got some things that don't do anything, we've got some things at lower pH, we've got some things that raise pH, and you want to be able to use this table to do stuff. So if I remember, let's go ahead and use tin. Tin is SN. Okay, and I'm going to do tin nitrate, okay, NO3. Nitric acid is a strong acid. What is the charge on tin? And you're just going to look at the table here. I shouldn't maybe pick something where you need to look at the periodic table, but the periodic table doesn't help you as much when you get that far down. So what's it say the charge on tin is? No, don't look at the periodic table, look at the chart.
2 plus.
Plus 2. Okay, good. So we know it's plus 2 based on the chart. Okay, and then what's the charge on nitrate, which you should have memorized, but you can also look up on the chart? -1. Okay. How many nitrates do I need with how many tins to make it neutral? 2 nitrates, right, to make a neutral compound. Now, I'm not going to scroll over to the side because it's going to mess up the way these things present. But this stuff is it's a salt. We're going to assume it fully dissolves in solution, right? So we have aqueous. And why? I know that nitrate's really great at everything. Any nitrate thing is supposed to dissolve. So I'm going to end up with tin 2 plus, right? Plus, how do I do? Go write the next bit on your own. How do I do that? Common mistake here, but I'm trying to catch a common mistake. Okay, what I'm hoping you wrote is you took this 2 and you put it in front to show that I have 2 nitrates. They don't stay together. So this means I have 2 nitrates. They're not staying together. They're floating around on their own. I get that. And the nitrate, I need to not forget, nitrate has that negative charge on it. Okay? Excuse me. All right, so now I go to my table. What is tin going to do when it dissolves in water? Lowers pH. Okay, lowers pH. What does nitrate, according to the table, do? Does it raise pH? What does it say here? No effect. Okay. Okay. So if one lowers pH and the other one has no effect, what happens? pH lowers. Questions?
What are you considering large and small? Like, when you're saying small highly charged cations, like, where would you cut that off?
Oh, here?
Mm-hmm.
I think they're just telling them here are some small, highly charged cations. In other words, so that's what this, I would read this table. That's a good question. In terms of, this is not a, hey, all small, highly charged cations. This is a, these are small, highly charged cations.
So it isn't all small highly charged cations, but
It's just this.
okay.
Okay. In terms of looking at the periodic table, though, you know, it sort of makes sense. There's very little way down the periodic table on this list. I can reason why a lot of those things would be small and highly charged. I can't reason why all of them. Okay. But what I'm asking you to do here is I would give you the table. Small, highly charged cation refers specifically to these. Okay. Questions? Okay. So you should be able to use the table. And here I've got this figure from your book. I thought it was really illustrative of this concept of why weak acids are weak and why strong acids are strong. How we can think about this in terms of stability. So for a weak acid, what's going on is for the dissociation reaction, the products have a higher energy than the reactants. Okay, these things are weak. You have to go uphill in terms of getting a higher energy to get these things dissociated. So there's going to be less of this than there is of this, if that makes sense. You are going to be reactant favored because the reactants are more stable. Go ahead and write that. Reactants more stable. Why don't you start thinking about things in terms of stability because they're at a lower energy there. When we have a strong acid, so we know hydrofluoric acid is a weak acid. We know that hydrochloric acid, the acid in your stomach, is a strong acid. Okay, and so that's because the products are more stable. So we make a lot of these because they are more stable than those. Okay, questions? All right, so, and this is using these energy diagrams we've used before, right? We've used these before. You were going to see these. If you continue on with chemistry, you're going to see these again and again and again. They get used in all the classes. Okay, let's talk about something else. So rather than use the table, we don't need that table to do all things, all right? So I might give you the table and ask you to do things based on that. But if we want to think about the strength of an acid, we can actually use periodic trends to do that. So we're going to use periodic trends to predict acidity. All right. And so when you look at the periodic table, as you go across to the right, and this is going to be all looking at the conjugate base. Okay. So looking at the conjugate base, things become more acidic in this direction, and they become more acidic in this direction. Okay? So what do we mean by that? If we look at our periodic table, right, fluorine is here, okay? Chlorine is here. Oxygen is here. All right, if we think about a couple different acid-base reactions, we could think of, about hydrochloric acid, right? Hydrochloric acid is going to, actually, we know it's a strong acid, so we're going to draw it like this, H plus Cl minus. Okay, hydrofluoric acid goes to make H plus F minus. Okay, I'm not going to make a big deal. I'm trying to get these arrows correct in terms of strong acids and weak acids. I'm not going to make a big deal with how you do your arrows, right? Spend your brain power elsewhere, but in this class. Sorry, guys. I'm having too much fun up here. Sorry. All right, so HOH, which is water, right? Water, but water can be an acid, and we can make H plus OH minus, right? Let's look at our periodic trends here. What do? They say that if we look at our conjugate base in each of these, right? Here's our conjugate bases. If we're looking at our conjugate bases, as we go this way and down, things become more acidic. So this would be the least or most acidic. Water would be the least or most acidic of the three. Least. And then more, right? Because we're going up. We get more acidic in this direction. So more, not up, but more, and then more, right? So this tells us that things should get more acidic in this direction. And what I'm talking about is these acids become more acidic as we move up because that follows our periodic trend to the right and down. Questions so far on the trend itself? We're going to explain why. Let's go check that one real quick, though. We had a table up above, right? And this figure from your book. Does this agree with the figure for our book? We had water as the least acidic, right? And then hydrofluoric acid as next, and then hydrochloric acid. Okay? Follows our periodic trends. Excuse me. So you need to be able to use that table. You also need to be able to use periodic trends if not given the table for what's a stronger acid, what's a weaker acid. Questions? Okay. I had another thought there. Oh, I just wanted to emphasize. So OH minus, is that very stable or not very stable? It's not very stable, which means it's very reactive. Okay? And OH minus, if you have a concentrated solution of hydroxide, you should be scared of that. That's dangerous. Okay? Gotten the impression talking to you folks that they haven't given you anything too concentrated in the lab yet. All right, so let's come back down here. So we've got these trends. So why? Why are these trends? So this is an example of those trends right here. Okay, we'll talk through this and then we'll talk about why. But why is that the case? Or not why is that the case? But here we have the same sort of thing. So this is offensive to me that we're even calling this an acid, but you know, You can use that, right? You can look at the periodic table. Carbon is a really weak acid. It's not likely to give that up that H. And in fact, in this class, you should plan on it never gives up the H. Okay, that can't be your answer if you get asked for a trend. But NH3 is a stronger acid. Okay, neither of these even make our table. So these are acids under super, super crazy conditions. Okay, and then finally, water kind of makes our table. We know water can self-dissociate a tiny bit, and then hydrofluoric acid dissociates more. And that follows, that's our trend right across the top there, right? As we go from left to right on the periodic table there, carbon's weak to the strongest of those four is the fluorine, the HF. Yes?
Why is it written as H3N instead of H3NCH4?
Here,
Yeah.
these are these acting as acids. So this giving up a proton, if it gives up a proton, it's going to have to become negative, and we have H plus comes off.
Well, I was asking why is it written as H4C instead of CH4? Because
Yeah. So they're trying to show it as an acid is what they're doing, right? The acidic. If we consider these to be acidic protons, right? When we put these H's behind there, you never pull them off, right? So they're just following what this is. And when you go to organic, they're not going to do that. Okay, so we've got this trend from left to right. What's going on there? So from left to right on the periodic table, the effective nuclear charge is increasing. All right, so if I come over here and look at the periodic table, we're going from left to right, all right? And so if you remember, effective nuclear charge is something we covered in the first semester. And what it says is that you've got these protons in the nucleus. And our inner shell electron, effective nuclear charge is the charge, let me write that down. Effective nuclear charge is the charge that outer shell electrons see, okay? What's going on then is if I think about, let's think about sulfur actually. Sulfur has how many outer shell electrons? 6, 1, 2, 3, 4, 5, 6 outer shell electrons. Those 6 outer shell electrons, the charge on the nucleus is 16, right? 16 protons. But the 10 inner ones, we have 10 electrons in the inner shells, right? 8 here, 2 here, those are fully shielded. We have inner shell electrons that fully shield those outer shell electrons can't see any of that charge. And then for this is a simplistic model, but it works well. For this model we're using, these six proton charges get through, and you can see those. The effective nuclear charge is 1, 2, 3, 4, 5, 6 for sulfur. Okay. For our examples up above, we're upper row, so the inner shell but it's the same. 1, 2, 3, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine. Okay. So as the effective nuclear charge goes up, those atoms are going to pull electrons. They're not going to want to share as much. They're going to pull electrons away from the attached hydrogens. So if we think about HF, right, going to HF going to H plus F minus. I'm going to go and put all my electrons on here. This has all the electrons here. It has the fluorine is sharing these two electrons. It has an effective nuclear charge of 7.
Is that the ZF?
Yeah, it's the Z effective of 7 right there. So it's a high effective nuclear charge. So it is going to be pulling hard on these electrons in the bond. And those electrons in the bond are more likely to pop out of the bond and onto the fluorine to make this happen. And far, 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 far more likely than what would happen if you had a methane. This is natural gas. Think about the natural gas that comes out of the spigots upstairs or may heat your dorms. I guess you guys may have pumped water, but it's actually natural gas underneath, probably. Okay, and so far, far more likely than for this to happen. Okay, because the effective nuclear charge, let me make that a better arrow. I'll go ahead and I'll use the Z effective here. And that's 4. Just count over from the left. Okay, so this is much more acidic. Yes. What is Z effective? Effective nuclear charge.
Oh, okay.
Let me go up here and I will add Z effective right here so that we know. Questions? Okay, so that's one thing that's going on. So that's the left to right, but what about the up to down? That's right, it's going to be size of something that's going on there. So, and we've got that going on right here. So compounds become more acidic. Moving down the periodic table because the conjugate base is bigger. And the minus charge that's acquired can be spread out, okay? All right, so we can think about this in various ways. But when we look at this example right here, where it's got bromine, chlorine, and fluorine, we're going to get more acidic as we move down the periodic table here, because those electrons have more space to move around it. All right. If I have a negative charge and a negative charge, what happens to them? Well, they're going to repel each other, right? So fluorine is more unstable with a negative charge than bromine because the fluorine's small and those negative electrons have to be close to one another, as opposed to bromine where they have more space. Does that make sense? Okay, so that's why we have a down as well. Questions? Yes?
So when you're talking about that, like the additional space, does that mean there's more room for the electron density to change and therefore it's easier for it to pop off the hydrogen? To make it, like, make the solution is more.
I agree with the first part. So do I mean there's more room for the electron density to change, right? But I want you to think about not so that you can pop it off, but I want you to think about the stability of this. This is more stable than this. So it's pulling more on the electron. And in fact, it's pulling less because it's farther away, right? But once you make your Br minus, it is more stable because this negative charge can be delocalized around the atom. It's bigger, right? As you go down the table there, we keep going to outer and outer shells, and each shell are bigger and bigger shells, because as you add a shell, it becomes, it's an outer shell. You have your first shell, you have to put the next one outside of it. Does that make sense? I think about it in stability, okay?
But it's just its ability to hold on, right? Like, this, what's making something acidic is if it loses its hydrogen, like the solution, right? Am I thinking about that in the correct way?
So I'm not thinking about it as ability to hold on to the hydrogen. These arguments aren't about ability to hold on to the hydrogen, they're about the electrons.
Okay.
Okay, so I'm not saying you're wrong in terms of thinking about the ability to hold on to a hydrogen. Okay, yes, a stronger acid doesn't hold on to its hydrogen as much, but the arguments I'm making here are all about electrons, not about the hydrogen. Now they extend to why something would grab a hydrogen or not.
Oh, okay.
But we're thinking about these from the perspective of electrons, and the perspective of electrons interacting with the base, right, the conjugate base, not from the perspective of the acid holding on. That makes sense. Questions? Other questions on that? Okay, that's good question. And we use different explanations. There are multiple good explanations for certain things in chemistry. We use different explanations, and we all use a model, and we switch around which models we're using based on what's best for the current situation. If that makes sense. Doesn't mean there's a gazillion different models, right? What I want to emphasize, what I hope you're getting out of this class, is we're going to have a small number of set of rules, and we're going to try to apply them everywhere. The smaller the number of rules we have and apply everywhere, the better. Okay, right? Okay, so let's go ahead and when I grabbed this problem this morning when I was working on my notes, I was offended. And for some of it, I wasn't sure what to do, actually, even. I figured, we'll solve it in class. And so we will. Okay? But so here what we have to do is we have to pick on, so this is like all the problems I do in class, where this is the even numbered problem, there's the odd problem above it that is the same concept. Okay? And you have the answer for it. And that even number problem, those even number problems are fair, those odd number problems are fair game for quizzes and tests. I'll try to use them as much as possible. But here what we're trying to do is figure out the strongest base, right? We just had a set of rules for how acidic something is. How do I apply how acidic something is to how strong a base is? It's the opposite. The stronger the acid, the weaker the base, right? The weaker the conjugate base. All right, so looking at these things up here, what we want to do is we're going to go, okay, I've got a CH4 and an NH3. Using my rules on the periodic table, which of these is the stronger acid? NH3, right? More acidic as we go to the right. So which of these is going to be the strong, if this is the stronger acid, which one's going to be the stronger base? That, right? Does that make sense? All right, how about this? Fluoride and chloride. If we were thinking about the acid here, right? Think about the acid here. Which is going to be the stronger acid? Hydrofluoric acid or hydrochloric acid? Hydrochloric acid. So which one's the stronger base? Fluoride. Does it make sense? Okay. How about this one? Water versus hydrogen sulfide. Which one's going to make the stronger acid? Okay, H2S. And so what I'm doing here is I'm just pointing to H2S, right? But if we're thinking about these as conjugate bases, officially, it works either way. We would be thinking about this versus this, right? because these are the conjugate bases of those. But does it change how we apply the periodic trend? It doesn't, right? Both of these, so this is going to be the stronger acid. Oh, wait, yeah, that's a stronger acid, so that's going to be the stronger base. And then finally, the most offensive of the bunch, the one where I wonder whether, I wonder whether this is true or not even. I'm not sure because suddenly there's not H's there. Do they mean to put H's there? I kind of think maybe they did and it's a typo. But regardless, if I saw this, let's say I'm taking a standardized test, okay? And I see this and I'm like, what the hell? Okay, sorry. But what is going on here? Well, I'm just going to apply my rules, right? Which of these would be stronger? Pretend it's hydrogen or don't pretend it's hydrogen. Who cares? Which of these is going to be a stronger acid? It's not kidding, be an acid. But it's going to be the O is a stronger acid, so that's going to be the stronger base. Okay. And looking at this, I really think because we're talking about stronger acid that they meant to do that. Okay. I don't. You essentially, I guess you plopped an extra electron on there somehow. You could do that under extreme conditions. So I'm not sure if that's a typo or not, but just apply it. Apply our rule, okay, to the other atom. Questions? Okay, so where are we at? We've got almost 20 minutes left, which is awesome.
I love this.
There you go, great.
Biology is too hard.
Let's go ahead and, so now I want to talk about some cases where we don't apply those periodic trends, some special things that happen. Okay, we've got two things called resonance and inductive effects that also affect the strength of bases, or strength of acids. So acids are also, or acid strengths, let's say, are also affected by resonance, which we talked about last semester. I'll give you a resonance, and by inductive effects. So we'll talk about what both of these things are here. And so let's consider two different molecules. Let's consider ethanol. Okay. Ethanol can be an acid. Go ahead and draw the products of that. All right, so hopefully for ethanol, what you're showing is that this proton would come off, okay? The reason I know that this one comes off is because if I go up to the periodic table and I go across the right, oxygen is farther to the right. There's a higher effective nuclear charge, so it's more likely to lose its H plus. So this would be this. Okay, plus H plus. And then down here we have acetic acid. Okay, once again, we'll have the H on the O comes off. Really never on the carbon. Okay, you might get a problem where you get no choice, in which case you have to do it. But really extreme conditions are necessary to pull a hydrogen off of a carbon. All right, so this is acetic acid. Acetic acid is a much, much stronger acid. It's still a weak acid. But ethanol is a super weak acid. All right, why is that? Well, what I have is this thing called resonance. I have this right here, and I can make two structures. I can put the double bond here, I can put the double bond here, and they look the same, and this, it turns out, is really stabilizing. And you should have talked about resonance in your classes last term, briefly maybe.
Is it because they share that like three, it's like a 3.5 or whatever across the two?
The way I like to think about it is I can show where I can move the electrons around without moving any atoms around and breaking any rules. So what I can do, when we think about resonance, these electrons can come down here to make a double bond, and these electrons can pop up here, okay? And that's how I get between these two structures, okay? And this is very stabilizing. Whenever you can do this with a molecule and show multiple forms, I don't know what I just drew there. All right, so whenever you can, so resonance is very stabilizing. Okay. When we think about this, depending on how you've been taught it before, so we can draw this as this or this, right? Once again, it's just a model we're using. In reality, it's a mixture of the two. Okay. So, but that's very stabilizing, and so our base is much more stable, and so our acid is much more acidic, right? If this is much more stable, you want to go this way compared to the thing up on top. Still weak acid. Does that make sense? All right, so that's our resonance effect. We can also have inductive effects. So an example of an inductive effect would be as if I put fluorines onto that acetic acid. So I'm going to make trifluoroacetic acid. The fluorines are on the carbon, so this is not like hydrofluoric acid where you have to run for the hills, right, where you have to have your antidote next to you. And so I've got fluorines on the carbon over there. And so I can go ahead and deprotonate this as usual. Whoops, I can't replace my fluorines though. Fluorine, fluorine, like that. Okay, so now I can deprotonate here, but what's going on in terms of the stability? I'm not going to draw it, but it still has resonance. Okay, I'm going to leave it out for time in terms of drawing it, but you see we can do the same resonance thing we did before. But on top of the resonance, what do you know about fluorine? It's super electronegative, okay? It is the most electronegative. Electronegativity increases as you go to the right and go up. It is the most electronegative element on the periodic table. All right, so what that means is it really wants electrons, and it's pulling the electrons from the side. So if we think about over here, we're going to be, because we have fluorines, you can imagine we're going to be pulling to all of them. We're pulling electrons towards them. If we pull electrons towards these, we're pulling them away from the oxygen. And the oxygen is like, hey, I don't want to share with that. And so it's going to grab those electrons off of the hydrogen. Okay, that makes this base more stable. That's more of a way of thinking about how tightly it holds onto the hydrogen in terms of that model. Okay? But do you see that? So inductive effect. Okay? Fluorines pull electrons away from the oxygen. And the oxygen takes the electrons in the bond. Does that make sense? So we're pulling electrons away from this oxygen. Oxygen says, hey, sorry, hydrogen, I'm taking those electrons. Somebody took my electrons, I'm going to take yours. Yes?
Is this only with fluorine, or is it anything that's like more electronegative than
It-
hydrogen?
It's anything more electronegative than carbon.
Okay.
So anything more electronegative than carbon is going to pull electrons away from the carbon will pull more away from this carbon. You can get an effect over there. But fluorine will give you the largest effect because it's the most electronegative. Good question. Other questions? All right, so we have those two effects. So let's see, we have 9 minutes left. What I want you to do with your I want to talk about titrations. I'm not going to have a lot of time, so I'm going to blow through it. So let's just do one problem out of this one. Go ahead and let's go ahead and do the first one. You're supposed to make the most stable conjugate base, meaning you're going to take one proton off. Where does it come from? Do A. I'll give you 30 seconds, and then we're going to quickly start into titrations. Okay, so hopefully what we've got here is, if we look at our table here, we've got atoms we can take hydrogens off of, right? I can take them off of carbons. Is there anything to the right or down of carbon on it in there? Oxygen is the right of carbon, right? So I can take it off of oxygen. Is there anything to the right or down of oxygen on there? Sulfur. So I go to the right and down. Sulfur is what I end up with as the most right and down. And so that's the proton I'm going to take off. So my conjugate base, I'm going to put all my electrons in. Like that. Does that make sense? We used our periodic trends there. Okay. And you could do the same thing for this one. And this one's going to be resonance. Okay, so what I want to do now is I want to start talking about titration. As I understand it, you've done titration a number of times in lab, and you're going to do it again in a couple weeks. Okay, so titration is a technique that you can use to figure out the concentration of an acid or a base. Okay, the way this works is, okay, a known concentration of a strong or weak base is reacted with a unknown concentration of a weak or strong base. And I put these in the right order. Base. Then stoichiometry happens. Then you do stoichiometry at it. Did I miss one? I'm sorry. Concentration of a strong or weak acid base. Very good. Is going to, and then I'm going to do acid base down here too because I slipped I flipped acid base. Okay, so we're gonna do an example here so you can see this. But the important thing here is remember in a neutralization reaction is a neutralization reaction. In a neutralization reaction, a acid and base react to make water and a salt. Okay, and then the other thing to say is that if one of those acids and bases is strong, the reaction goes to completion. Okay? All right, if both are strong, it also goes to completion. So let's go ahead and do a problem here. I've got like 3 or 4 minutes, so I'm going to kind of blast through it so you can see it today. This is important stuff. It's also complicated, so we will go over more examples on Wednesday. But here I've got a solution of cesium hydroxide that's analyzed by titration. It's found that that many liters of that molar nitric acid, which is a strong acid, is required to neutralize that many liters of the base. What's the concentration of the base? And so this is going to be a stoichiometry problem where we're going to go with, we've got a liters of base, right? So we're going to go, well, we're going to use that base, but we're going to start with what we know. So we've got a volume of acid, okay? We're going to go to moles of acid, okay? We're going to then go to moles of base, and then we're going to go to concentration of base. All right. The conversion factor here, volume to moles, is concentration of acid, which we're given in the problem. Moles to moles is going to be our balanced equation. Okay, and moles to concentration, we're going to use our volume of, in this case, base to get that. All right, so looking at this, let's go ahead and write out our balanced equation because we're going to need it. Cesium hydroxide, I can look at the periodic table on my left and see cesium is, and at your right, is going to has +1 charge, so that's going to be what the formula is. That's going to react with nitric acid, which is our strong acid. And it's going to go to completion, so I'm going to go ahead and make water. Plus, I'm going to make a salt, which is going to be cesium nitrate. Like that. That's my balanced equation. And now I'm going to go ahead and apply, try and keep that right on screen there, what I've got. So I'm going to start with the volume of acid. I have 0.0824 liters of nitric acid. Okay? If I have 1 liter of nitric acid, super quick, how many moles do I have? It's 1.5 molar. So it means I have 1.5 moles in a liter. Okay, that's a conversion factor. 1.5 moles of HNO3. Okay, if I have 1 mole of HNO3, how many moles of cesium hydroxide does it react with? 1. Okay. So 1 mole HNO3 reacts with 1 mole of cesium hydroxide. Okay, now if I'll now have moles of cesium hydroxide, I want to get concentration, right? So I just need to divide by volume. I could pop out the moles and then divide by volume, or I could just divide by volume here. I am almost done. So that's my volume of base, right? So I'm just going to go ahead and divide by 0.00250 liters, right, of cesium hydroxide. And moles, moles, liters, liters, I'll put that into my calculator really quick here. 0.0824 times 1.5 divided by 0.025 equals 4.94. 4.94 molar cesium hydroxide. Okay? That's how you do that. I will post this. I'll post the video. I know I had to do it really quick there. All right. And we'll talk more about titrations on Wednesday. You guys have a great couple days. If you need help, please come and see me.